Integrated communication systems eliminate the traditional Snoopy cap headgear that astronauts wore for decades inside their helmets. The XAMU suits designed for the Artemis program feature a new audio system built directly into the helmet structure, ensuring consistent audio quality regardless of head position or movement during complex tasks. Previous suits required separate headsets with foam earpieces and microphone booms that could shift during movement, creating dead zones where astronauts couldn't hear or be heard clearly. The integrated communication system includes speakers mounted inside the helmet and several embedded voice-activated microphones that automatically pick up when an astronaut is talking to mission control or crewmates. These voice-activated systems distinguish between intentional communication and background noise, breathing sounds, or casual conversation that shouldn't be transmitted. The microphones use advanced noise cancellation technology that filters out the constant hum of life support systems, fan noise, and other mechanical sounds that would otherwise interfere with clear communication. Multiple microphones provide redundancy and enable the system to maintain clear audio even if individual components fail. Advanced audio systems provide crystal clear communication despite the challenging acoustic environment inside pressurized suits. Space suits create noisy environments filled with the constant sounds of fans, pumps, motors, and airflow that can overwhelm traditional communication systems. Modern audio processing uses digital signal processing algorithms that automatically adjust volume levels, filter background noise, and enhance speech clarity in real time. The systems can distinguish between different types of sounds and prioritize human voice frequencies while suppressing mechanical noise that would make communication difficult. The helmet design provides improved acoustic isolation that enhances communication quality while reducing fatigue from constant noise exposure. Better sealing around the neck and improved internal padding reduce external noise intrusion while creating more controlled acoustic environments inside the helmet. The audio systems use directional speakers that focus sound toward the astronaut's ears rather than filling the entire helmet volume with audio. This targeted approach reduces overall noise levels while improving speech intelligibility during extended missions. Modern suits integrate simultaneously with multiple communication networks that operate on different frequencies and protocols. Astronauts can maintain contact with their immediate crew members through short-range radio links while simultaneously communicating with spacecraft systems and ground control through separate channels. The suits automatically manage these multiple connections, routing communications to appropriate destinations based on content and priority levels. Emergency communications receive automatic priority routing that overrides routine traffic and ensures critical messages reach their destinations immediately. The communication systems work seamlessly across different spacecraft designs and space agencies that use incompatible radio protocols and frequencies. International Space Station operations require suits that can communicate with Russian, American, European, and Japanese systems simultaneously. The suits include software-defined radios that can be reconfigured to work with different communication standards without requiring hardware changes. This flexibility enables crew members from different countries to work together effectively while maintaining contact with their respective ground control centers. Heads-up displays integrated into helmet visors provide visual communication capabilities that supplement traditional audio systems. These transparent displays show text messages, system status information, and navigation data directly in the astronaut's field of view without requiring them to look away from their work. The displays can show communications from multiple sources simultaneously, using different colors and positioning to distinguish between routine updates and urgent messages. Augmented reality features overlaid digital information onto the real world, providing context-sensitive data about objects and equipment in the astronaut's environment. Backup communication systems ensure astronauts never become completely isolated from safety networks, even when primary systems experience failures. Secondary radio systems operate on different frequencies and power sources, providing redundant pathways for emergency communications. The suits include emergency beacon systems that automatically activate if life support or communication systems detect dangerous conditions. These backup systems can operate independently of main suit power, using dedicated batteries that provide several hours of emergency communication capability. Emergency communication protocols automatically route distress signals to multiple destinations simultaneously, ensuring that help requests reach ground control, nearby crew members, and spacecraft systems even if individual communication paths fail. The backup systems include automated distress messaging that transmits astronaut identification, location data, and basic telemetry even if the crew member becomes incapacitated. The increased activity in space operations drives the need for these advanced communication systems. NASA's current astronaut corps includes 46 active astronauts representing unprecedented diversity in backgrounds and expertise, with commercial crew programs bringing additional complexity to communication requirements. The year 2025 saw over 200 EVA hours, double the 2018 figure, reflecting the growing scope and complexity of space operations. Since the International Space Station's assembly began, astronauts have completed 248 EVAs, each requiring flawless communication systems to ensure mission success and crew safety. Better communication directly improves safety and mission success by enabling faster response to emergencies and more effective coordination during complex operations. Clear, reliable communication allows ground control to provide real-time guidance during challenging tasks and enables crew members to coordinate their activities more effectively. Enhanced communication also reduces the psychological stress of isolation that can affect astronaut performance during long missions far from Earth. Next-generation communication features will transform how astronauts work by enabling real-time collaboration with experts on Earth and other crew members across vast distances. Upcoming systems will support high-definition video streaming, three-dimensional mapping data, and interactive augmented reality that connects astronauts with remote technical support teams. These advanced capabilities will enable complex operations that require expertise not available among the immediate crew members.